Hello everyone and welcome to this video in which we continue talking about the field effect transistors. If you remember, in our previous video we talked about the junction field effect transistor. Today we'll talk about the MOSFET transistor. So what is a MOSFET? A MOSFET is an abbreviation of metal oxide semiconductor field effect transistor. So simply it's another category of field effect transistors. And there are two basic types of MOSFETs. One is called the enhanced, or they give it the symbol E, enhanced, and the depletion field effect transistor. So it's the enhanced MOSFET, and we have the depletion or D MOSFET. Now, of those two types, the enhanced MOSFET is the mostly used one in industry and very similar to the bipolar junction transistor or to the junction field effect transistors. These are all transistors that can be used as either amplifiers or they can be used as switches. So the schematic symbol for two types, one is called the N channel and the P channel of an enhanced MOSFET, looks like the figures here. So this is for an N channel, and you can see that what we have here, we have a gate, again we have a drain, and we have a source. But the interesting thing is that you can see that there are broken lines between the drain, the source, and the gate, and this means that there is an absence of a physical channel. And of course, the inward arrow is for the N-type or N-channel E MOSFET, and the out arrow is representing the B-channel E MOSFET. Now, if I look at the characteristics of a MOSFET, and mainly we'll start with the E MOSFET, the characteristics looks like this. As you can see, we should be having a certain drain current, because if it's a switch, if this is working as a switch, then it will be representing this circuit as this. If there is a current ID flowing, this means that it's working as a short circuit, or there is a switch closed. And if it's open, of course, it will look like this, and the drain current will be equal to 0. So this is open, and here it is closed. Now, if you look at the characteristics, you can see that for a voltage less than the threshold voltage between the gate and the source here, for a voltage less than a threshold value, a positive threshold value for the N channel, there will be no drain current, which means that the switch looks like it's an open switch. And the minute you reach this threshold value, you start having a drain current increasing, and this increase is of course a parabolic increase. The same thing for the B channel, but it will be in a different way. However, the equation that can be used in order to calculate how much drain current I have for a certain gate source voltage is represented by a constant K, VGS minus VGS threshold, all squared. Notice that this value is a constant for a certain MOSFET. Now, the constant K can be determined from the data sheet, as we'll see in a second, by taking the specified value of ID, called ID on, at the given value of VGS, and therefore we substitute it, we get the value of K, and then after that we will be able to use this K to calculate any value of ID for any value of VGS, as we will be seeing in the next example. Now, I will give an showing here the data sheet for the group, which is 2N3796 and 97 MOSFET transistor. Of course, this is an N channel of the D type as an example, and it shows you here that the numbers like the maximum ratings you have to be careful about. As an example, you have a drain source voltage VDS is 25 volts for this type of transistor, 20 volts for this type of transistors. If we are talking about, as an example, the drain current, it's equal to 20 milliampere. Be careful about the units. If you are talking about the total power dissipation, it would be 20 milliwatts at temperature 25 degrees centigrade, and if you have any temperature above that one, then each degree centigrade will have a derating of the power by a value of 1.14. So as an example, if we are talking about the temperature of, let's say we are operating at 40 degrees centigrade, then this means my new power will be power in new, it will be reduced, and it would be equal to the value that you have here multiplied by the temperature. So the power we have temperature, which is a new 40 minus 25 degrees multiplied by the original power that we have, of course multiplied by 1.14, and here you have the original power, which is 200 watts. 200 minus these values, so this would be reducing, or the amount of reduced power in my case. So we have to be careful about the voltages that we are talking about for the off characteristics and for the on characteristics, as we will be seeing in this next example. The example says that the data sheet for a 2N7002 MOSFET gives that ID on is equal to 500 milliamperes, which is the minimum current to make it on, at a voltage VGS equals to 10 volts and VGS threshold equal to 1 volt. Question says determine the drain current for VGS equals to 5 volts. In order to solve this problem, of course, the equation is easy. You can say that the ID is what we are interested in. ID is equal to, if you remember, we said it's K times VGS minus V threshold all squared. Now, in our case, in our example, we do have what's the value of we know what's the value for V threshold given in the question. Here is V threshold 1 volt, so this is 1 volts. Again, I know what is VGS for my case. It's equal to 10. So this is 10 minus 1 squared. The problem is what is the value of K. I can get K from the numbers given to me. He's giving me ID on at VGS equal to this value, and therefore I can get what will be the value of of K. So first we find K. Simply, I will say the substitution will be that ID is equal to the 500 milliamperes. So I have 500 times 10 to minus 3 is equal to K, which is unknown for me. VGS given to me 10 minus 1 squared. Now from this equation I can get what is K, and that would be 500 times 10 to minus 3 divided by 10 minus 1, and if you calculate you'll be able to get that this is 6.17 milliampere per volt square. Milliampere per volt square. Now I can use this number in this equation, and I will say that ID will be equal to the value, which is 6.17 times 10 to minus 3 multiplied by 5 minus 1 all square, and that would be equals to 98.7 milliamperes. So it's as simple as this one. So if I just look now at the diploid MOSFET characteristics, it's a little bit different, and you can see that we have again the N channel and we have the P channel. Let me concentrate on the N channel, and you can see that for a zero value of VGS, you will be having your ID equal to the ID DSS, and for any value in the negative, of course, -1, -2, -3 VGS, you will be having a corresponding value of the current ID. Again, the equation is a parabolic equation, it's the same equation that we have in our previous example. So if we take another example, the example says for a certain diploid MOSFET, IDSS is given to be 10 milliampere and VGS, which is off, is equal to -8 volts. Now the first question says, is this an N channel or a P channel? Of course, I can tell right away that this is an N channel because you can see that VGS is equal to -8 volts. For the N channel, VGS is equal to negative. For a P channel, VGS will be positive. So for sure the answer will be that this is an N channel without say. The next question says calculate what is the value of what is the value of the current drain current ID for VGS equals to -3. Again, the equation here is very straightforward for part B, because already we are given what is the value of IDSS. So the equation will be ID is equal to, if you wish, IDSS, which we had before, 1 minus VGS over VGS off and squared. And if we do that, we will be substituting for 10 times 10 to -3 y minus VGS, which is -3 over -8 whole square, and for this case this is equal to 3.91 milliamperes. Now if you would like to try the case for VGS positive, which means that we are in the right side, in this case it will look like for part C, I will have again it's equal ID is equal to 10 times 10 to -3 multiplied by 1 minus plus 3 divided by -8 whole square, and this would be 18.9 milliamperes. Now we have what we call it the biasing of the MOSFET, which means how we are getting the voltage for the gate of the MOSFET. So we have what we call it E-MOSFET biasing, and because E-MOSFETs must have a VGS greater than the threshold in order for it to operate, then VGS threshold 0 cannot be existing. I cannot accept it, because if you have it as 0, then there will be no biasing. Now if you look here, you have two ways of biasing. One is called the voltage divider bias, which means that you can see this is the drain voltage, and here I have a voltage divider. So the voltage here that will be activating the gate will be equal to R2 over R2 or plus R1 multiplied by VDD. Or you can see that we just take it directly from here, called drain feedback bias. So directly the feedback is taken from the drain circuit here. So in either the voltage divider or the drain feedback bias arrangements, the purpose is to make the gate voltage more positive than the source by an amount equal to the threshold value. That's the most important part. So we said that we can get it simply by what? By saying that VGS, which is the voltage between this point and this point here, if you wish we can just draw it this way, VGS, this VGS is equal to, using the voltage division rule, it's R2 over R2 plus R1 multiplied by VDD, and we can say that the voltage VDS, which is the voltage here, VDS will be VDD minus the drop across this resistance, which is ID times RD. This is ID. Okay, so we can just at the end write that the current ID will be equal. In order to get it, it will be again the same equation that we had before. It's K VGS minus VGS threshold whole square. In the case, which is something interesting here, in the case of the drain feedback bias circuit, it's worth mentioning that there is negligible gate current, and therefore no voltage drop across RG exists, and therefore we can say that VGS is equal to VDS. So VGS here, VGS will be equal to nothing but VDS. So the voltage that is here will be equal to the voltage that is here. Okay, let's take an example here. It says for this circuit, determine the voltage VGS and VDS. We say that this is VGS and this is VDS. Okay, assuming that this particular MOSFET has a minimum value of ID on equals to 200 milliamperes, VGS equals to 4 volts, and VGS threshold is equal to 2 volts. So the solution is easy. The first thing we said that VGS from voltage division rule, we said that it's equal to R2 over R2 plus R1 multiplied by VDD. And if we substitute, this is 15K divided by 100 plus 15K multiplied by 24 volts, and the answer will be equal to 3.13 volts. Now to determine VDS, we said that VDS is nothing but VDD minus ID times RD. Okay, we know what is VDD, we know what is RD, we need to get what is ID. And we said in order to get ID, I need to get ID. We said the equation for ID, if you recall, it was nothing but K multiplied by VGS minus V threshold GS threshold squared. Okay, I know what is my VGS. It's 4 volts given to me. This is at 4 volts. Okay, or it's no, this is not 4. This is no, it's the VGS that we are operating is this value. So VGS is known. The threshold value is known, given to us as well. It's 2 volts. So let me just put a different color here. So this is our here is 2 volts. This 2 volts will come here, and this 3.13 that we just calculated. And all what we need to get is just to substitute. But how about the value of K? Now this K, as we just did before, we can calculate K from our equation that we had before. We said K can be written as, or we have the equation says ID, okay, on, we said that is equal to K VGS, again the same one as here, minus VG threshold all squared. And we are given how much is this ID on, because this is from the data sheet. This ID on is given to us in the question, equals to 200 milliamperes. So I will just substitute 200 times 10 to minus 3 equals to K. VGS corresponding to this value is equal to 4 volts minus the threshold to square. That implies that K is equal to 50 milliampere per volt square, 50 milliampere per volt square. And therefore I can go back to this equation and say, okay, then ID is equal to 50 times 10 to minus 3 multiplied by VGS, which is equal to 3.13 minus 2 whole square, and we calculate our current to be 63.8 milliampere. Now I can use this value of current in the equation, which is this equation here. I can use this current into this equation here. Correct? We'll just say V, then VDS is VDD in the question, 24, minus ID, we just calculated 63.8 times 10 to minus 3, multiplied by the resistance, which is 200 ohms. And that will give me my voltage, which is 11.2 volts. Okay, the last example, I will just use it for the case where we have a drain current, or where we have the case of drain feedback configuration. You can see here an example. It shows you simply that you have a MOSFET, it's a drain feedback configuration. VDD is equal to 15 volts, RD is given, RG is given, and you can see that you have a measurement for what? This measurement shows you VDS. We said that in this case, the question says that the threshold value for VGS is equal to 3 volts. And if you remember, we just said for this case, which is the drain feedback, there will be no current in the, there will be no gate current, and as such, we will be having VDS is equal to VGS. And from the measurement, it gives me that this is 8.5 volts. Because you can see this is connected between the G and the source, which is the ground here. So that would be 8.5 volts. And we said if this is the case, then it's so easy. If I know what is VDS, I know that VDS is nothing but I can get, because of that VDS is known, it's the voltage between this point and this point. So VDS is given to be 8.5 volts. And I'm asking you what is the current that is flowing here in the drain. So this current in the drain is nothing but this voltage, VDD, minus VDS, divided by RD. So ID is VDD minus VDS divided by resistance RD. And if you do this, these numbers, these are 15 minus VDS, which is 8.5, divided by RD, which is equal to 4,700 ohms, and that would be 1.38 milliamperes.